Okay, so I'll talk about representing centrality measures using coalitional games and using a representation that is basically able to incorporate the skills and tasks into centrality measures. And I will give, as an application of the whole mindset, two new measures of what I call helping centrality. And helping centrality is the idea that someone may be able to help a coalition, not because he's able to do things, but because he knows other people who can do that. Now, the paper does have substantially more results than the ones that I present here, and I'm not going to give many details. I'll put a link at the end of the presentation if you want. So our starting point is something very simple, and that's the notion of centrality measures in social networks. So here you have a graph, a network of important families in medieval Florence, and basically how they were related. And you can see from this example that some nodes are more important than some other ones. And one name which you definitely know of all these families is the name Medici. And if you look at this node, it's pretty well connected. You know, it has kind of a central position in the network because it's connected to a lot of other families. So the notion of centrality in a measure, in a social network, tries to answer this question: how central is a node in some form of a network? Okay, so we want to put a number which measures the importance of a node. And this has been done in many, many, many ways. There are too many that I cannot present all of them. I'll concentrate on a few of them. So let me give a couple of examples of definitions. You won't necessarily see how they are important, but if you want to see, for instance, in this scenario, the Medici is connected, has the largest degree. Okay, so it's central because it's connected to many other nodes. But that's one way to model centrality. And that's known as degree centrality. So the degree centrality of a node is basically its degree, appropriately scaled so that the centrality is between 0 and 1 in this example. But there are other ways in which nodes may be important. For instance, a notion called between centrality measures the extent of which a node lies on many shortest paths. So basically, for a node Y, its between centrality is the sum over all other pairs of nodes X and Z of the percentage of shortest paths between X and Z that go through Y. Okay, so if Y is central, is between many other nodes, it captures a lot of flow between the nodes. So that's another way of stating that a node may be central in a different way. One which is less obvious and harder to define is what's known as eigenvector centrality. So here is basically something on linear algebra. Basically, what we do is we take the adjacency matrix of the graph and we compute the eigenvalues, and the matrix is symmetric. Eigenvalues will be real numbers. We take the largest eigenvalue and we compute the eigenvector corresponding to it, and that's the centrality of the node. It's the value of that eigenvector for the particular component, and this is not very easy to digest intuitively. I will say that it's quite close to what happens in PageRank, in Google PageRank. And if you want to know more details about centrality, I've linked here to YouTube videos, which are from a MOOC on Coursera by Matthew Jackson, which teaches networks and centrality networks. And these are two links that you can try, and I will send the slides to anyone interested if you want to find more information about centrality. So centrality is one aspect of what I'm interested in, and I want to represent measures of centrality. However, the study of centrality has gone, as this was a subfield of graph theory or of experiments on networks and such. And from the point of view of sociology, this is not quite right. I mean, a person intuitively is not central just because it's well connected or powerful. It's powerful because it can do many things. So centrality is not only about the position in the network, but about what this position lets you do. Okay, this is like a philosophical thesis. Now the question is, okay, how do you model that? How do you model this? Okay, so there is no element of what you can do in many of the measures of network centrality that I talked about before, but it's suddenly important when we're talking about nodes in a multi-agent system. And the answer that I want to give is based on ideas from coalitional game theory. Now, I don't expect you to know about coalitional game theory, so let me give you a brief tutorial. So this is a part of game theory, and what we have is a set of players, and the players may create coalitions. And the goal is to get value by joining the coalition and then dividing the value that they can get between themselves. So we have a function v from all the possible subsets of agents to real numbers, which is basically v of s, is the value of that players from coalition S can get if they associate, irrespective of what the other players do. Okay? So I collaborate with you, we can get this much, and nothing that the other players are doing can change that. One example, consider a scenario where you have 3 players and they want to agree on something, and you need majority to vote, for your proposal. So empty coalition has value 0, cannot do anything. Coalitions consisting of 1 person also cannot do anything. They don't have majority, so their value is 0. On the other hand, all coalitions of 2 people or more can impose something. So the value, we model that by saying that the value of such coalitions is 1. Okay, so this is a specification of all possible subcoalitions that could form. Presumably in this scenario, we want to eventually everyone join the coalition. Okay, and it's how much, say, 1 and 2 get if they associate, and they get the value 1. And the main question in coalitional game theory is, okay, they associate, they form the coalition, they get collectively some value, the largest, the big coalition of all players. How does one fairly divide the payoff among members? Okay, so the coalition got something, now you want to divide that between members. So there is a very classical way of measuring how much should a player get, and it's the name of a Shapley value, and you have a complicated formula there, but let me try to demystify the formula for you. Let's imagine that you go to a bar with friends, and the amount of drinks you buy determines the price you pay. The more drinks you order, the cheaper they will get. And let's say, for instance, that the first player comes and it orders some amount and it pays for it. Now the second player comes and it will tell the first player, and I see that there is a problem here. The second should get the cost that the first two players would pay minus how much the first did play. Okay, so it's the difference between how much they would have to pay jointly versus how much they pay the first one already played. And the last player basically pays how much the Grand Coalition would pay minus how much the players without this player would pay. Of course, now, if you're taking such a scenario, the last one has an advantage because presumably by the time he got there, the price already went down. So he's going to pay less. So this is not fair. And to make this fair, you have to average this scheme of each player getting its marginal contribution, that is the difference between how much the coalition before the player plus him got minus the cost of what the players before got. And you have to average over all possible permutations of the player. So this is the Shapley value. Shapley got a prize in Nobel Prize in Economics, and it's the standard notion in coalitional game theory and economics, and it has axiomatic characterizations and all sorts of other nice properties. So this is fairly well established. Now, I want to use Shapley value in the following context. I have a graph. I have players are the nodes in the graph, and I have some sort of coalitional game on the nodes of the graph. And one particular type of centrality can be seen as a Shapley value of that game. Okay? So the setting is the centrality of a node is whatever the Shapley value tells it is. One such example is the following game. So imagine you have a graph, and the value of a coalition is the number of nodes in the coalition plus the neighbors. So it's how many neighbors, how many nodes is a coalition able to get to. This was actually used in other research, for instance, for finding nodes that, well, kind of spread epidemics. Although it's not the kind of epidemics that we're talking about today, but this was a Suri and Narahari paper they were using such a measure for. Okay? And versions of this measure have been used, and you'll see this immediately, for, things like identifying important nodes in terrorist networks. And suffices to say that this game theoretic network centrality, that is the Shapley value of the game that I just talked about, has a very easy interpretation. It's basically the following. Each player gets one unit, and then he or she divides a unit equally between the player and its neighbors. So he keeps 1 over its degree plus 1, because that's the fraction. It divides it equally. So he sends this amount of 1 equally to the neighbors, but also receives this amount from the neighbors. And what he gets at the end is the game theoretic centrality of this node. So that's a game theoretic measure of centrality. And this is a formula for the one before. And the question that I want to ask in the paper is, in a certain sense, are all centrality measures the Shapley value of some game? There is already an answer to this question, but it's kind of an artificial yes answer. And anyway, this is very impractical. If you remember what I told you what a coalitional game is, to specify a game, you had to give all the possible values for all the possible subcoalitions. So if you have, 10 agents, you can do, but that's like 2 to the 10 subcoalitions. That's 1,000 coalitions. But if you have 100 coalitions, forget it. So this representation, to give a game, you need to specify 2 to the n values. Okay, which is not practical. So in the multi-agent literature, there's been quite a bit of work on what's known as concise game representation frameworks. And my proposal in the paper was to use one such representation and see what it is good for. And it happens to be one which employs the notion of skills and tasks. So remember that what I said before was that we should include actions that players are able to complete as a result of associating to a coalition. So coalitions have actions that they would be able to complete. So the framework that I'm going to present and study does that. Okay, so this is the following framework. It's by the name of Coalitional Skill Games, and it's again well established in the literature. There is a set of skills, and there is a set of tasks. You'll see an example immediately. Each task may need some set of skills. And if a coalition is able to perform a certain task, it gets some profit out of performing that task. So the value of a coalition is obtained as follows. People in the coalition pull together their skills. They perform all the tasks that they have the skills to do, and they get the profit. So the value of the coalition is the sum of profits of all the tasks that could be accomplished by the coalition. And in a certain sense, Bachrach et al., which introduced this model, proved that you can simulate every coalitional game by such a coalitional skill game, which does not specify, it specifies the value of a coalition implicitly. You don't have to give you have a way to compute the function, the value of a coalition. You don't need to give it. There is an algorithm for it, which you can use for this. So a first question is every centrality measure the Shapley value of some coalitional skill game? Well, let me give you one example. So imagine you want to model the number of edges in a graph. That's my centrality as a node. And you want to get it as a Shapley value of some game. Let me tell you what the game is. Players are the nodes in the graph. Skills correspond to edges. And if I am one of the two vertices on an edge, I have that edge skill. Tasks are also the edges, and they bring profit of 2. Okay? So now when is a coalition able to perform a task? When it contains at least one of the two endpoints of the edge. So it's a number of edges that are covered by vertices in S. Now if you compute, that's a simple exercise, the Shapley value of this game, then basically what happens is that the task, the value of each task, which is 2, the profit, gets divided equally between its endpoints. So each node gets a value of 1 from each edge it's adjacent to. So the Shapley value of each node is exactly the degree. Okay? Let me give you a more informative or intuitive example. So post 9/11, people in the political science literature have looked at terrorist networks. And there is such a well-known study due to Krebs, which assembled the network of contacts of people that hijacked the airplanes on September 11. And the scenario that I'm presenting is a version of one that was used in other papers in the literature. So in this scenario, you have the nodes in this network, and nodes may have one of two skills. They're either pilots or no martial arts. Of course, there are some nodes which don't have any skill, like 16 has no skills. And a coalition of nodes is said to be able to carry an attack if it contains at least 2 people that know martial arts and at least 1 pilot. Okay? In other words, in this example, players are the nodes, skills are being a pilot or knowing martial arts. There is only one task, attack, and that is a multi-set of 1 pilot and 2 martial arts. And the value of a coalition is 1 if it contains enough nodes with such skills and 0 otherwise. Okay, so this is a way of modeling a scenario like this using a coalitional game. Okay. So let me come back to the question that I had before. And the question was, is every centrality measure the Shapley value of some coalitional skill game? Remember that Bachrach said that every coalitional game can be simulated by a coalitional skill game?
Yes.
And, sorry? I don't hear you well enough. Okay, so every coalitional game can be simulated by such a game, and every centrality measure is the centrality of a coalitional game. So you might expect that the answer to this question is yes, and it is yes in an unnatural way. But the more interesting part is that the answer is no. With a sudden restriction, there are some properties that all coalitional skill games have, and eigenvector centrality doesn't. So you cannot represent eigenvector centrality as the Shapley value of a coalitional skill game with rational profits, whereas you can represent degree centrality and between a centrality like that. I've already shown you degree centrality, so let me give you a few details on the actual property that I mentioned. The property is the following. It's basically being a rational function. So I'm going to encode edges, pairs of nodes, into a Boolean variable, which is a 1 if I have an edge, and a 0 if it's not. Also, a vertex will be encoded as a Boolean variable, which is basically 1 if the vertex is present in a coalition and 0 otherwise. And I'm going to say that a centrality measure is rational if it's basically the quotient of 2 polynomials with rational coefficients. Okay? So that's a definition of a rational centrality measure. And eigenvector centrality is not rational for a very simple reason, that all the values of rational measures have to be rational numbers, whereas eigenvector centrality has some irrational values. So that's very easy. But let me show you, for instance, that degree centrality is rational. So indeed, I just put P of a vertex to be the sum of variables of all the edges that are adjacent to the vertex, and Q of n is 1. More interestingly, between a centrality is also rational, and here the proof is a little bit trickier. I basically first encode the path as a monomial by multiplying the variables on the edges of the path. Then I encode as a polynomial the fact that I have a path between 2 nodes and no shortest path exists. So this variable x p tilde tells me it's 1 if p is the shortest path between its endpoints and 0 otherwise. And then I can basically encode between a centrality by encoding all the sums of xp tildes into the appropriate polynomials. So it's quite easy to see that between a centrality is rational, a rational function like that. The family of characteristic function is rational. It has a similar decision. So many games start with a value that is rational itself. And a measure induced by a family of coalitional skill games with constant coefficients is rational. Centrality measures induced by rational characteristics functions are rational. For instance, game theoretic network centrality is such an example. Eigenvector centrality is not rational. So eigenvector centrality cannot be represented by coalitional skill games with rational coefficients. And it's an interesting open problem to extend the class of coalitional skill games to be actually able to capture eigenvector centrality. So to some extent, this result was surprising because everything in the literature was pointing to the fact that, yes, you might be able to represent everything as a Shapley value of some coalitional skill game, and you can't really. So let me go to the second part, which is actually more interesting, and it's about new measures of helping centrality. Let me give you one example, which is all too familiar to people that have been serving on the program committees of conferences. So if you're on a program committee, you need to get each paper to receive, say, at least 3 reviews. And you get tons of papers, and you may be able to use sub-reviewers. So you may lack the skill to review a paper. However, you're very valuable to the program committee if you have enough friends that have the skill to review the paper. So you're not necessarily helpful because you know to read all the papers, but you're well connected enough to people that have the necessary skills. So this is the kind of phenomenon that I want to measure. I want to put a numerical value. I have a network of people, and they have some skills and tasks, and they're able to get their friends, the neighbors in the network, to help them complete the tasks. How much central are they, with respect to how good are their neighbors? Okay, and it's actually not very, very easy to do. So a first approach was to try to get a coalitional game, which basically starts from a coalition and adds all the neighbors of nodes in that coalition, and then you get another game, and you take the Shapley value of that second game and you remove the Shapley value of the original game to remove, I want to measure not how much am I contributing to solving tasks, but how much are my friends contributing. So you should remove my own skills from that. So this was a very natural idea, but this doesn't work because sometimes this has negative values, and intuitively you shouldn't have happen that because the node may be able to not to help, but it shouldn't hurt. So this is not a good solution. Another idea which doesn't work starts basically from the simplest game you could consider. Each player has some weight, and the value of the coalition is the sum of weights of the players in that coalition. So if I compute the Shapley value of the helping extension of this game, then I get a formula which is not important, but it's important in the following sense. It has the first term involves the actual vertex, and the second term, the sum, involves only their neighbors. So if you want to disentangle the value of the player itself in accomplishing tasks, you should remove the first part. So this suggests that the appropriate measure would be something like this: the Shapley value of the extended coalition minus the first term. Again, this doesn't work. It has negative values. So let me give you 2 ways. I mean, it's one way, but there are 2 measures, 2 related measures which work. So the idea is to come up with something like a Shapley value, except that here I add also not only the previous, I order all the nodes in the coalition, I add the node, and then I add all the neighbors. Okay, so it's a generalization of the Shapley value for the graph where every node is disconnected. It has some nice properties. For instance, it's non-negative for monotone games. However, it doesn't quite capture the whole idea that node eyes should matter, skills should matter. So a second version of this measure is called helping centrality, and instead of subtracting only the nodes before node I, I'm also subtracting I, because I only want to capture how much are my neighbors bringing to the table. And of course, the second measure is the first measure minus the Shapley value, the ordinary Shapley value. Okay? So these are my 2 measures. there are some nice results and there are some not so nice results, but in a certain sense, they do have some properties which are reminiscent of the Shapley value of the ordinary one. They're hard to compute in general, but they can be efficiently computed under some natural restriction on the game. And I'm not giving you a theorem at this point, which says that because it would be too technical. And it has some other properties which are sort of generalization of what happens to the Shapley value. So let me give you this example, which we mentioned before. Let's compute helping centrality. So remember the two measures were helping Shapley value and helping centrality. And in the helping Shapley value, I wasn't subtracting the value of I. It was the value of I plus the neighbors. And in helping centrality, it was only the neighbors. Okay, so let's compute these measures on this network and see if the results are somewhat interesting. Now, anyone can tell me intuitively which is the most connected node in this network?
Five.
Or maybe 16. Look at 16. It has a lot of connections, and all the neighbors of 16 could start an attack only on their own, basically. 5 can't quite, I mean, it certainly cannot do that because 5 does not have 2 neighbors which know martial arts. So in a certain sense, 16 has even more. It is even better connected because its neighbors could start an attack, whereas the neighbors of 5 couldn't. 5 doesn't have enough neighbors among people that know martial arts. But the intuition is okay because this is what we're going to see. So here I have the tables, and I'm going to discuss them immediately. For the helping Shapley value, for the helping centrality, and for the ordinary Shapley value. And your intuition about 5 was right in a certain sense, but not for, not quite for the helping nature of it, but for the actual connection. So let's see what the Shapley value, the ordinary one, is telling us about the network, just the regular one. And there is a notion here that basically helps reduce the computation. Basically, their 2 nodes are called equivalent, and they have the same skills, and their neighbors have the same sets of skills. So from their local point of view, everything is the same. Whatever one brings to the table is whatever the other one brings to the table. So this partitions a set of nodes into classes, and of course, nodes in the same class will have equal values. Okay, so Shapley value is not about helping, but about the value of individual players. So what Shapley value is telling us is the following. It's more important to be a pilot, more critical to be a pilot, than knowing martial arts, and that's more valuable than not being able to do anything. Okay, so if you look at this last table, this is what the ordinary Shapley value is telling us. It's nodes that are pilots, 5, 7, 9, and 12, which are the most important from the point of view of their own skill. So being a pilot is more important. Then comes all the yellow nodes, which are martial arts. Then come all the white nodes, which have no skills. Okay, so that's what the ordinary Shapley value is telling us. What about helping Shapley value? Again, in helping, the centrality of a node includes also what he or she can do, but also what the neighbors can do. So it's all of them. In this scenario, it's the 3 nodes that are pilots other than 5, so 7, 9, and 12, that come up most central. And that's because, for instance, 9 knows 2 people with martial arts and a pilot, or it doesn't even need a pilot. The 2 people with martial arts and the node itself can start an attack. So basically, these 3 nodes, 7, 12, and 9, are the most helpful. What's the least helpful node? The least helpful node is node 2. And that's basically because no neighbor of node 2 has any useful property, knows anything. So it cannot bring that much to the table. It's not a pilot. It brings some because it knows martial arts, but it's not, it doesn't bring anything from the neighbors. So it's least helpful. Finally, and this is helping centrality, and this is where it's somewhat interesting. So if you subtract how much a node can bring to a coalition by joining the coalition from how much the neighbors of a node, then the most the most helping node is node 16, which on its own doesn't know anything, has no skills, but knows tons of people with skills. Okay? So it knows 2 pilots, it knows 3 people with martial arts. The neighbors of this node are the most central ones. Okay, so this is not necessarily paradoxical because 16 was viewed to be central in other ways. Say, for instance, it's the most well connected. But here I'm also looking not at the connection only, but what the nodes can do. What's more interesting, though, is that, say, node 13 is more, central in this example than 7, 9, and 12. And the point is the following. Yes, it's 7, 9, and 12 that are most central when their contribution is tallied. This is what I showed in the previous slide. But we don't care about that here. We remove the contribution of a node. We only care about what the contribution of the neighbors of the node is. And in that sense, nodes 7, 9, and 12 help more, but they also have valuable own skills, which basically are subtracted in the formula. Remember that the helping centrality is a helping Shapley value minus the Shapley value. So I would state that this measure is somewhat interesting, although clearly more experience and more data. We do have codes to run this on multiple data. The trouble with doing such experiments is not the lack of codes, it's a lack of data. Basically, it's hard to get data that is labeled with skills explicitly in the literature, because partly the literature has not recognized this fact that the literature has treated networks as all there is about society, and that's clearly not the case. So I will stop here. If anyone is interested, you can take a look at the version of the paper on the archive. I can send you the version that will get published. And I'm basically ready at this point to take questions. So please ask them. Directly using a mic.
Well, if none is starting, I will start with a question concerning eigenvector centrality. I somehow missed the fact it's a number eigenvector centrality.
For each, yes, for each vertex, there is a number.
Yeah, because on the slides where it was presented, it appeared that W is an eigenvector, and I was a little bit confused.
So W is an eigenvector, and it's a vector which has one entry per vertex. So
Yes.
W of Z is the
Okay. So in fact, the components of the eigenvector
yes.
are used as centrality measures.
Yes.
Okay.
Yes.
I understand.
The components of that vector.
Yes, the components. Yes,
yeah,
it's
and
true.
again, if you look at the videos of the classes that I have alluded to, it's actually much more intuitive. But then I would have spent a lot of time to do the computation. So if anyone is interested, those types of computation are very similar to what people are doing with PageRank computations. So it's kind of related to PageRank, although PageRank has more, it's a linear combination of identity matrix plus. So we want to massage it, but the same type of computations gets. And it's quite used in, for instance, there is Network X, which is a Python package for computing these centralities. And I did play with computing centralities like eigenvector centrality and other centrality measures for social networks for different reasons. So you can suddenly use this, not helping centrality directly, but the other measures like eigenvector centralities are implemented already in measures of, in social network packages or tools like, PIEC. So there are other tools for network analysis which can compute such measures.
Okay, thank you. May I ask another question?
Of course.
Concerning the helping centrality, it's a difference between two Shapley values in some sense. So can it be interpreted like some kind of a gain, like is, for instance, in the context of information gain or something like this?
Well, I don't know about that, but it's, my instinct would be to say no, but I don't know. I don't know if this is true for the Shapley value in any, the way you would answer this question is by answering whether the Shapley value itself has some information theoretic interpretation, and that I don't know. If the Shapley value has, then this one, which is a generalization, basically one of my measures reduces to the Shapley value if the graph is a graph consisting of isolated nodes only. Because what I do is I factor in not only what I bring to the coalition, but what my neighbors are bringing to the coalition as well. And if there are no neighbors, then they don't bring anything. So if that has game theoretic information theoretic interpretation, then eigenvector centrality also has an information theoretic interpretation.
Well, I don't know. I also don't know, but okay.
Okay. I know this is quite theoretical, and I sort of like, it's a little bit difficult to, so the bottom line is that there are frameworks for representing centrality measures. They have nice properties, sometimes unexpected properties, and they're able, if you think of centrality measures in such terms, you're able to model more things than you would normally model, and sometimes come up with measures that are moderately interesting. That's sort of the point that I want to get at, is that I'm proposing going beyond simple looking at links, going, representing explicitly what agents are able to do. And that is something that is not captured simply by a network. And I claim that that is interesting enough to be, captured by representations, like, of social phenomena. So not only what the nodes, who are you connected to, but what can your friends do or help you do. And there are classical results in social theory, like there is something called strength of weak ties, which talks about the fact that we get our information from nodes that we don't have a day-to-day contact with, but from people that are casual contacts. And that's basically because with people that you interact a lot, you tend to have the same type of information. So it's people that are far apart from you that are able to tell you new information. So in a certain sense, the ability of telling you something is correlated to the fact that you're not connected to those people by a strong link. So that's sort of one way to interpret this strength and weak ties property.
Okay, and the last question would be related to the fact that I'm wondering if such an analysis could be applied, for instance, for biological networks, like functional networks or networks expressing relationships between proteins or something like this. Have you found something in this direction?
I mean, I don't know, because I'm not I don't have a big background in biology, but maybe, I speculate now, if A is neighbor to B, and if B can catalyze some reaction, so if there may be scenarios like that where being connected to someone helps you do something.
Well, usually in biological networks, connectivity means, in fact, interaction in some sense.
Mm-hmm. No, but I'm thinking more in terms of like catalysis or stuff like that.
Yeah. Yes, I understand. Yes. Yeah.
So,
in order to help some processes. Yeah.
I mean, I mean, it's certainly worth looking at it from this point of view, but I haven't really. I mean, I'm interested in many things about network centrality, but for this, you'd need to work with a biologist or someone who knows this stuff well. So
yes, that's true. That's true.
I can't really. I don't want to really speculate on applying this to an area which I don't know much about. So probably I can.
Okay, thank you.
Any other questions?
In terms of applicability, how computationally intensive is evaluating such a model? And what would be a reasonable data scale in terms of the set of skills and how many nodes we can have in the graph?
Okay. So Shapley value in general is expensive. And if you compute it naively, it bottoms out easily to like 20 nodes or 30 nodes. That being said, there are number one scenarios where computing something like that is easier than the general case. And it's certainly true, for instance, there is a result which I didn't present it, which says that if the number of skills, the maximum number of skills you need in a task is limited, there is a constant upper bound on the number of skills you need for a task, then basically you can come up with dynamic programming algorithms for such computations. So yes, it's hard in general. To be really honest, I haven't really, being the first paper that talks about this, I didn't really try the whole issue of how far they scale, although I do expect that roughly when methods work for the Shapley value these days, it will work from a measure. So it's going to be no worse than that. It's going to be essentially, there are scenarios where computing the Shapley value is easy, and I do believe that in many cases, this is not going to be computationally very difficult. So I don't expect, I don't have example. My problem with being more applied here is a lack of good data. You give me some good data on networks that are marked with tasks and skills. So give me, please, a good, data to work on, and I'll guarantee you that there is a lot of interesting stuff to do. And my bottleneck is that the data is not usually labeled with the information I have. So it's suddenly interesting and it's potentially useful, but I haven't really done that.
Thank you.
Any other question?
Yeah, I would like to inject one if possible.
Okay, I guess if not, then I can thank you all for being here, and I will actually place this video on a link if you want to see this one on YouTube on a private link. If anyone wants to see it, please send me an email, and if you also you want to see the paper, me or Cosmin can send you the. It's not yet out. We've submitted it, but it's going to come probably in May or something like that online. There is the technical report version of it, not the final publication. Okay.
Gabi, I'm sorry,
Thank
my
you.
microphone was off. Can I still inject one question? Maybe
Yeah,
it's short.
of course.
Okay, so is it my first one to clarify something? It's my understanding that this centrality measure will give me kind of a value of which is the most important node in order to achieve a task. Is that correct?
Well, not to achieve a task, but to. No, it's what's the most important node in bringing your friends to achieve a task.
Okay, excellent. So then my question actually refers to what happens. Is this we assume from the beginning that all the tasks and all the nodes are friendly, right? Or
No.
can they
No.
be adversarial nodes in there?
Well, I haven't really done anything in adversarial framework. That's certainly interesting.
So you think it would complicate a lot of things because they would be interesting?
Okay, for instance, one thing that I didn't do in this particular version, and it's certainly interesting, is that in my version, I didn't care that a coalition was not connected.
Okay.
So technically, the Shapley value has a version, which is called the Meyerson value, which takes into account connectivity of coalitions. Now, mine is a generalization of the Shapley value, and I could talk about connected coalitions. So yes, of course, you could try to generalize something like this to scenarios where you have adversarial behavior. In fact, I even had thought of, well, not necessarily the measure, but some frameworks which are based on this idea. I did consider the idea of generalizing this. To a certain extent, one thing that is important here is you stay with some literature. So if there is one point which I did, this was my first paper in this area, basically, in this direction. Not in the area of cooperative game theory, but in this idea, it was the first paper that was talking about centrality measures. And suddenly you can do a lot of stuff, and we can discuss offline if you need more pointers to the literature, and if you're interested, because people are doing quite a lot of work in centrality measures in networks and in real scenarios or pseudo-real scenarios or stuff like that. So there is a lot of work to do in this area, basically.
Okay, I guess I'm gonna catch up with you some other time and get into some details. I'm more interested about what happens when you have adversarial networks
Mhm.
for social networking, for example. That's purely the case. Maybe for biology and chemistry, it's more. You can assume that everybody's more cooperative. I think I'll get back to you on this. Thank you.
Yeah, so yeah, hopefully we'll meet physically in not too long a time.
Oh, that would be awesome. That would be awesome.
Okay. Okay. Any other question? If not, thank you all here for being here tonight and
Okay, thank you very much, Gabi. The master students are kindly asked to stay a little bit more. I still have to mark the presence, so around 5 minutes, please.
Okay.
Please stay online, the students. Okay, thank you.